Hello, everyone, and welcome to the third live session of our 8-part webinar series, Seismic Design in Steel, presented by Rafael Sabelli. This session is Design of the Moment Frames. Today is September 24th, 2018. My name is Nate Gonner with AISC, and I am your moderator for today's presentation. I would like to introduce the presenter and author of this webinar series, Rafael Sabelli. Mr. Sabelli is a principal and director of seismic design at Walter P. Moore in their San Francisco office. He is a recognized expert on seismic design of steel structures. His experience includes the design of new structures, the retrofit of existing buildings, nonlinear seismic analysis, and the development of new structural systems. He participates in many national technical committees responsible for building code development, including several such committees here at AISC. Rafael, welcome back, and I'll now turn it over to you.
Thank you, Nate. Welcome back, everyone. As you just heard, today's session is the live session 3, the design of the moment frames. As a reminder, our course objectives go back to understanding the principles of seismic design of steel structures and extend to application of those principles to both steel special moment frames and buckling restrained braced frames. And we will go over the design requirements as well. As always, I'll remind you that there are other resources available to you, including the AISC Seismic Design Manual, the latest edition just published, Ductile Design of Steel Structures, and the AISC Facts for Steel Buildings publication number 3, Earthquakes and Seismic Design. You also have the Solution Center available to you and a special address for webinars at AISC. We have already covered in this class, in the recorded sessions, some of the general principles for ductile design of steel structures, including in session 2, a general treatment of the design of moment frames. Then in the live sessions, we've set up the building example, we've planned out the seismic design and done the basic seismic analysis, and now we are ready to proceed with the design of the moment frames. And then next week we will finish up with the design of the braced frames. So with that, let's begin session 3, design of the moment frames. In this session, we will talk about pre-qualification issues, that is the pre-qualification of the beam to column connection for a special moment frame. Some analysis issues, some issues related to the design of the connection, and we will also cover frame optimization. After that, we'll proceed to design the beam, check the beam for strength, check the column for strength, and then proceed to a base plate design and discuss what is left undone to complete the design. So our design example will go through the base plate design, but we'll also discuss what we didn't cover in the example at the end. All right, I will remind you that my advice is to treat the moment frame as governed by the drift demands. So that is to say, the drift limit will be the governing concern in selecting our frame member sizes. Our beam size and our column size will be selected to keep drift under the drift limit. Generally, a special moment frame has a strength demand capacity ratio that is well below 1. So it is advantageous to postpone our strength checks until after we are satisfied that we have the beam and column sizes that we want. So we'll optimize the frame for drift. We'll look at some other optimization things, and then we'll proceed to do the strength check for the beam and the column. It is very convenient to use software analysis software to compute drift. We've just discussed some of the modeling issues in session L2. And when we're selecting members to control drift, it's important to keep in mind that not every member is going to be appropriate for use in a special moment frame. There are pre-qualification limits, meaning that some beams will just be too deep, too heavy. They may be very efficient to use, but they are not pre-qualified, and therefore, or they are not pre-qualified for the connection that we intend to use, and therefore we shouldn't be spending our time selecting them only to find later on when we check our pre-qualification limits that the member is not acceptable. Similarly, the seismic provisions have compactness limits. We are required to use highly ductile members. Those have maximum B over T ratios for flanges and H over TW ratios for webs. And so we want to keep the members that we put into our model limited to the ones that will be acceptable for use for a special moment frame. We don't want to waste our time selecting a member that's efficient to use for the drift limit, but then isn't allowed to be used in a special moment frame. And finally, we also have a requirement in the seismic provisions that we maintain this so-called strong column, weak beam proportioning, so that the hinging tends to occur in the beam and not in the column. And so as we select combinations of beams and columns in our analysis software to control drift, we want to make sure that we aren't selecting too weak a column or too strong a beam. We want to make sure that the pairings work well together. Okay, for the example, we've selected this reduced beam section, or RBS connection. That's a fairly common connection type. It's also a connection type that provides a very good illustration of the design procedure. The analysis is relatively simple. There aren't too many limit states, and there are fewer limit states than you might see in some of the bolted connections. So we can get through it fairly quickly, but it's not too simple. The welded unreinforced flange welded web connection, or WFW connection, would be one that I would recommend considering for such a small building. It's a very simple connection, very easy to design and very easy to construct. So it would be an appropriate one to look at for the size of building that we have in this example. But the design procedure is maybe a little bit too simple to really be all that informative for the design of other connections. So the RBS connection is a good example. It may not be the one that you would end up using for all the buildings of this class, but it's one that you might use, and it's a good illustration. If you had as one of your criteria for selecting the appropriate connection type, if you have the criterion of eliminating field welding, there are a couple of other connections that you could consider: the bolted flange plate connection or the bolted end plate connection. Both of these are field bolted connections. And are preferred by some erectors because they don't like to spend time with the field welding. So in selecting the connection type to be used in the building, you might consider contractor preferences and capabilities, and also inspection and non-destructive testing requirements both in the shop and the field. So it's not very straightforward to say always use this or that type of connection. It's going to depend on who you're working with and what area of the country you're in. But each of these connections shown on this slide could be considered for this type of building, and I wouldn't say any of those is the wrong answer. In this example, as I said, we're using the reduced beam section connection. All right, so we've selected a pre-qualified connection. The pre-qualification document is AISCE 358, and it's going to give us some guidance on the system that we can use the connection in. So the limitations include limits on the member sizes. So you can't use the heaviest beam in the book because the connection really hasn't been tested for those extremely heavy beams. There's a limit on the degree of beam reduction, so we're cutting into the flanges of the beams, and that's been tested and established to work over a certain range, and we're going to limit ourselves to that range, as we'll discuss in a couple of slides. There are some analysis requirements because we are doing something to the beam that affects its stiffness. That affects the overall drift, and that has to be reflected in our analysis. And there's a design procedure outlined in AISC 358 that helps you go step by step and make sure that you've checked all the limit states and ended up with an appropriate design. There's some special detailing that's also covered in AISC 358, as we'll see, and lateral bracing requirements to make sure the beam remains stable. And of course, a protected zone where we expect inelastic strain in the beam material. So the member restrictions, these are covered in AISC 358, section 5.3. The beam has to be an I-shaped beam. It could be built up, but typically it's a rolled I-shape. 36-inch max, 300 pounds a foot max. The flange thickness is limited to 1 3/4 inches. And for a special moment frame, the span to depth ratio should be at least 7. So if you're lower than span to depth ratio of 7, the slope of the moment diagram becomes steeper, and it affects how the connection behaves and the demands at the face of the column and so on. But if the span to depth ratio is 7 or greater, the slope of the moment diagram is more gradual, and the connection has been established to work well. The beams that we use have to be seismically compact so that you can achieve full yielding and go through significant inelastic strain of the flange. However, because of the nature of the connection, where the beam is yielding isn't where the beam has its full flange width, but really in that reduced beam section connection, what's called the center 2/3 of the reduced beam section. That's where we check compactness, and we'll show that in a couple of slides. Also, we require lateral bracing near the hinge, just outside the hinge region, but that lateral bracing can be achieved in some cases via a composite deck. So that's something that many engineers take advantage of. There are restrictions on the column. The column can be I-shaped or a box section or a boxed wide flange. The connection, the reduction can be 25 to 50% of the flange width, and that has an effect of reducing the flexural strength of the beam about 15 to 30%, because obviously we're not reducing the web, and the web does participate significantly in that flexural strength. There are also dimensional limits that we have on the connection, as we'll see in a few slides. Okay, so here is a plan diagram showing the column and the beam with the reduction on each side of the web, the reduction of the flange on each side of the web, and that's of course top flange and bottom flange. In the RBS connection, we define a few dimensions here. A is the distance from the beginning of that cut to the face of the column, and there's a range that's permitted, the range over which the RBS is affected. If you're too close to the column, then the stresses are too non-uniform near the face of the column. If you're too far away, it's just not effective, and it's going to yield in the unreduced section of the beam. So this is the target range for that dimension A. There's a dimension B, which is the arc length of that cut. There's a dimension C, which is how much you're removing on each side. So 10 to 25% on each side would be 20 to 50% of that flange width. And then here's a handy equation for the radius of that curve. You don't really use that radius in any of the directly in any of the calculations. And here's an equation for the effective plastic section modulus with the reduction of those sections of the flange. So we start with Z sub x because Z sub x includes the entire section, including the fillets of where the web joins the flange, and we subtract out the effect of those two rectangular areas. Then we also have the check for compactness in the center 2/3 and the effective flange width. There's an equation here for the effective flange width that you would get at that 2/3 point, or 1/3 and 2/3 point, and it does include the radius. I'm not going to show you the derivation of that, but that's the effective flange width that you would compare to the requirements of AISC 341. So in the frame analysis, we need to modify some stiffnesses to reflect the reduction that we have. We've discussed panel zone modeling, how we're not going to do panel zone modeling, but instead we are going to use the full flexural length of the beam going to the column center line and the full flexural length of the column going to the beam center line. Second order effects should be included, and we will select members such that we meet the pre-qualification limits, and we also have an appropriate modeling of the base. So this is the frame model that we discussed already in live session 2. We have, based on the tech guide, the tech brief published by NIST, National Institute of Standard and Technology, a tech brief on seismic design of special steel moment frames or steel special moment frames. The recommendation is if you take the full reduction of the of that dimension C up to 0.25 times the flange width, then you have essentially 90% of the flexural stiffness of the beam. That's a reasonable assumption. So that's what we have in our analysis model. We also have, for the moment, a pin base, but with a flexural member here reflecting the flexural rigidity of the foundation. We are not modeling the panel zones. We're using no rigid end offsets either, and those two simplifications more or less offset each other. We've got the lower column modeled all the way up to the 3rd floor and the upper column from the 3rd floor to the roof. So we're not including in the model, say, the extra 4 feet or so that the lower column would extend up. That's a refinement you could make that might have some minor effect on the frame stiffness. And that foundation flexural restraint is reflected by a grade beam that we've put in here, with the note that when we get further along in the design, we could actually look at the rotational restraint provided by, say, a spread footing or whatever foundation system we put there. The second order effects are going to be addressed by calculating the B2 factor rather than modeling a leaning column in our analysis. We could do it either way, but I think for clarity we'll do it by the B2 factor. So here's the cover page of that NIST tech brief, seismic design of steel special moment frames. I will note that if you read the text of AISC 358, where it discusses the effect of the RBS on the frame stiffness, it says you can increase the overall drift by 10%. So that would be increasing the flexibility of both the beams and the columns by 10%. In contrast to that, the tech brief says just increase the steel moment frame beam by 10%. Don't increase the flexibility. Don't increase the column flexibility by 10%. So in other words, instead of increasing the overall drift, just model a beam that has 90% of the stiffness of the full beam, and that's a pretty reasonable way to go about it. The reduced beam section obviously doesn't directly affect the column. I will note that many software programs allow you to model the RBS directly, to put in how much you are reducing that, and the software does what it does best. sets up the actual stiffness, the elastic stiffness of the system that you're designing, and calculates the drift appropriately. If you do that, you will find that the RBS effect on the drift is often in the neighborhood of 2 to 5% rather than in the neighborhood of 10% as the AISC 358 suggests. So this is a very conservative assumption and not one that I would recommend. The NIST tech brief assumption of reducing the beam stiffness by 10% is itself a little conservative, but reasonable. And if your software can do it directly, by all means have your software do it directly. Okay, so here is the model that we have, or the loading that we have on the model already calculated in session 2. These are forces that correspond to CUTA, and they don't have the second order effect B2 included in them. To get the period, we want the tributary mass. So we have some mass at the roof and mass at each floor, and we can put that into our model and calculate the period. All right, so let's make sure that when we're selecting members, we use the appropriately highly ductile members as required by AISC 341 for the special moment frame in section E3. And we respect the pre-qualification limits that we just covered. So we're going to also, in our modeling or in our member selection, anticipate some other requirements, such as the strong column, weak beam requirement for special moment frames. And also we'll discuss the potential need for column reinforcement, such as continuity plates and doublers. That will become a little bit clearer towards the end of this part of the design example, but this is the appropriate place to consider it. Okay. So the pre-qualification limits are our maximum depth with that span to depth ratio of 7 or greater. We couldn't have a depth greater than 50 inches. That's fine. The RBS limitations 36, 300 pounds a foot, and so on. As a suggestion, and this isn't, actually we didn't do it in this design example, but this is the appropriate place to consider it. Look at the RY of the beam that you're selecting, because if your RY is, say, 2 inches, your maximum unbraced length for a 50 KSI material is going to be about 50 times RY, so that's about 100 inches. So a lateral brace at about 100 inches or about 8 feet, that seems okay. If you go lower than this, your lateral braces will have to be closer than every 8 feet, and there's a cost to that. So I will say that the beam that we're selecting will have braces closer than every 8 feet, and there is a cost to that. But it ends up being probably the right decision for this example. Okay, you can turn to the seismic design manual, and it will tell you for special moment frames which sections meet the requirements for compactness. However, that's for the full section. For the RBS, remember that we have an effective width based on the section cut that we use. So there can be some sections that are not covered in this table that will work for the RBS beam. If you wanted, and here's that equation again for the effective width, if you wanted to take advantage of those sections, you could assume an effective width of about 80% of the full width, and then check once you've designed the RBS connection later. Okay, strong column, weak beam. Here's the requirement from AISC 360. You need to do a number of things, as we'll see later, to get the moment capacity of the columns, do a number of things to get the moment capacity of the beams. It's pretty handy at this point just to simplify it by looking at the plastic section modulus of the columns compared to the plastic section modulus of the beam, including the reduction. And this isn't going to be 100% accurate. It's going to be biased, and I like to keep this ratio above 1.5. I find that if I keep this ratio above 1.5, I never fail strong column, weak beam. Probably you can come close. Probably in some circumstances you will fail, but at least most of the time it works, and even when it doesn't work, you're close to making it work with just a slight adjustment. I will say that if the stronger you make the higher you make this ratio, the less likely it is you will need column reinforcement. So we'll see later on that if we had selected 3, maybe we wouldn't need a doubler plate or continuity plates. However, this is only for, say, a W14 column. It doesn't really work for a deep column type of structure. All right, so we're going to assume that the RBS is reducing our flexural strength by about 30%. We'll select our members, but we will have to check strong column, weak beam explicitly later. There are sigmas in there, meaning you could have more than one column and more than one beam. And what does that mean? Well, for this connection, we have one column and one beam framing in. For this connection, we consider it 2 columns and 1 beam. This one would be 2 beams and 1 column, and this one 2 columns and 2 beams. I set up a spreadsheet for this design example where I simply took the ratio of those plastic section moduli, so I could select an appropriate combination of W14 column and W27 or W24 beam. And where the ratio was below 1.5, I said, okay, I'm in danger of not meeting strong column, weak beam later on when I do the calculation. And if the ratio is too low, I said it's very unlikely that I would meet strong column, weak beam. So keeping things above 1.5, I had combinations that I selected from. Okay. For drift, there are some traditional methods, such as published in Farzad Naeem's Seismic Design Handbook. Here's an equation for calculating the drift based on the height and length of the bay, the section, the moment of inertia of the column and moment of inertia of the beam, and the shear. You could set all that equal to the drift limit and then select appropriate beams and columns. You could make an assumption that the column moment of inertia is, say, twice the beam moment of inertia, and then solve for the beam moment of inertia and then the column moment of inertia and so on. That will get you pretty close. However, I will say that nowadays, with the analysis software that we have, it's pretty fast to hone in on a solution, through iteration. So I'll leave it up to you how you want to begin the process, but it is an iterative process to select members that will get you to your drift limit. So you could set up a computer model with some arbitrary size or some guess, and then increase or decrease stiffness to achieve the proper drift. Again, remembering to use the seismically compact members and trying to respect strong column, weak beam proportioning. Remember that the computer model, in the computer model, every time you change a member, you are changing the stiffness, and the stiffness will affect the period. The base shear changes with the period. So your period for drift can be a lot larger than CU times the approximate period. And the longer the period is, the lower the force is. So you want to be using the correct period to calculate the drift, because if you use the artificially low period to get your force, your building will be a lot stiffer than is required by the code. So the scaling of the forces changes with each iteration, because each iteration changes the members and changes the period. And use in many software programs design to a response spectrum. So the computer program calculates the period and then determines the appropriate force from the spectrum and then calculates the drift corresponding to that force. If we're doing it, say, the old-fashioned way, where we compute the period, get the drift, and then calculate the displacement, at the beginning, our CUTA for this system, our approximate period times that CU factor, put us about at a period of 0.9, which gave us a certain base shear coefficient. And then we would apply that force, calculate our drift, find that we were perhaps below the drift limit significantly, and select more flexible members, calculate a new period which was lower with a lower force, and so on. And as we iterate, we would approach a period of about 1.5 seconds, a lot longer than CUTA, and a base shear of about 60% of the original base shear that we had calculated for design for strength. So much more flexible, but this is the period that gives us the force, that gives us a displacement equal to our drift limit. I won't spend a lot of time on this, but as I said before, you could calculate a displacement spectrum, and with some assumptions, including this fairly arbitrary 2/3 factor that relates spectral displacement to roof displacement, you would approximate a period of about 1.4 seconds. All right, so here are our sizes that give us pretty close to our drift limit. Many software packages will allow us to use the RBS modeling. There are other methods for adjusting, say, the beam stiffness that have been published. The NIST method of using 90% of the beam stiffness, where you're taking the full reduction, that's pretty good, but that is a little conservative. It does overestimate stiffness significantly. All right, here's the period that we have. Here's the base shear coefficient based on that period. So here's the shear that we have for calculating drift. This isn't the appropriate shear for calculating the strength demands. And based on that force and the stiffness of the members that we've selected, we calculate drift ratio at each of these floors. That's using the C sub D amplification. And now we're going to amplify for second order effects. Remember that ASCE 7 requires us to amplify for second order effects, where the second order effect has a 10% effect or more. I say might as well just always include the second order effects, and where it's less than 10%, it doesn't have a big effect, and where it's greater, you've got it covered. So we're going to calculate this B2 factor based on the modified design that we have, and then we'll amplify the displacements by that B2. So here's the factor B2, more or less taken from AISCE 360. It has the P story, it has the displacement, and that's the displacement that corresponds to the shear that's applied. So this is the drift, the shear that we calculated for the drift check, and this is the unamplified drift that corresponds to this shear. Then there's an RM factor, which relates to how much of the force is supported by moment frames compared to the overall effect on the story. We're going to use the appropriate load combination, which includes 1.2 dead plus 0.5 live. And for simplicity, we'll assume that no more than half the load is supported by these moment frames. So that gives us this simplified equation where the drift is the drift limit and the RM factor is 0.93. And based on that, we calculate a different B2 at each level. It's typically largest at the bottom level, where it's 1.06. All right, that's good news because it's less than 1.1, which means we can use an effective length factor of 1 for our moment frame columns. That's almost always the case for a special moment frame. Right, so here's the period that we have for that final design. Here are the amplified drifts, amplified by that B2 factor. That gives us the final drift, and it's less than our drift limit of 0.02. There's just a little bit of margin there, so we're pretty efficient in our design. ASCE 7 has this stability check with this factor theta sub I. It's got a lot of stuff in here, but really the delta and the V should correspond to each other. The I sub E and the C sub D are just there to cancel out where the base shear was amplified by I sub E and where delta was amplified by C sub D. The maximum ratio we're permitted is given by this equation here. For a special moment frame, it's this part that typically governs. The beta factor is essentially the demand capacity ratio that we have. And we put that in, and for a special moment frame, we're not really permitted to have a theta greater than 0.1. We calculate the theta that we do have, and it's 0.07, so we're fine there. And as a reminder, there's a relationship between this B2 and this theta. It can be approximated like this. Actually, you can get closer if you include the RM factor. All right. At this point, we have a frame design. We have stiffnesses. We can check a couple of the irregularities. We take our displacements from our model. We take our shear from our model and calculate what's an effective stiffness here, the shear divided by the displacement. And we see that the stiffness increases as we go down the building, so we don't have the vertical soft story irregularity. We can check for weak story. For the weak story irregularity, we want the force, the shear in the column that corresponds to the plastic hinge formation. So we look at this little subassembly. We've broken things down into the subassembly for a number of reasons. Assuming we have a plastic hinge at the beam ends, we calculate a shear that corresponds to those plastic hinge formation. And via statics, we calculate the shear in the column that also corresponds to the plastic hinge formation. This gives us, when we add these up, this gives us the story shear strength. So adding them up, here's our story shear strength, just slightly higher at the roof, but then it goes down slightly and then goes up again at the second floor. So this is just because we can't have that weak of a beam at the roof. Okay, so we do not have the weak story irregularity. Okay, so at this point, we've selected members that meet the compactness requirements. They meet the RBS limitations. We have a frame that meets the drift limit and the ASCE stability limit. And we can use a K of 1 for our strength design and don't need to worry about having to use the direct analysis method. So let's proceed to the connection design. These are the members that we've selected. we're going to look at this connection, W14 by 132 column, W24 by 62 beam. Here are the section properties. All right. So we start by computing the beam plastic hinge moment. We analyze the beam to find the forces consistent with that, compute the forces on the connection, and check a number of limit states, including strong column, weak beam, presented here as a limit state, but it's a check. Certain beam checks that are in AISC 358, and certain column checks that come out of AISC 360, such as web local yielding for that concentrated force, web crippling, flange bending, and then the panel zone shear. The example more or less follows the 2010 provisions, but we'll comment on differences in 2016. So we start by selecting these dimensions A, B, and C. A, we're keeping near the lower end of that acceptable range. B, also towards the lower end of that acceptable range. These things keep the plastic hinge closer to the column face. And then C, we're more or less in the middle of that range, maybe towards the upper range, taking a fairly large bite out of the flanges. Our reduction is 27% of the plastic section modulus of the beam. And so applying that reduction factor, we get a flexural strength of the plastic hinge, 70-90. This includes a CPR factor, which is calculated thus per AISC 358, and it puts us halfway between yield and ultimate for the A992 material. All right, so in order to do the beam analysis, we need to figure out where these plastic hinges are, and that's where this dimension S sub H comes in. S sub H is A plus B over 2. So S sub H takes us from the face of the column to the center of the plastic hinge. To figure out the length between plastic hinges, we take the overall centerline to centerline length, subtract half a column depth on each side, and S sub h on each side, so the dimension A plus half the dimension B. And that gives us a length of 321 inches compared to the centerline length of 360 inches. The stiffness, as I said, that 10% reduction can be pretty, it's rough. It may not be enough in some cases if you have a really low span to depth ratio, perhaps for an intermediate moment frame where you can go down to 5. If you have really thick flanges and thin webs, which are really only possible for built-up sections, then this 10% reduction may not be very valid. In most cases, in most special moment frame cases, the 10% reduction can be pretty conservative. We have a higher span to depth ratio, typically well above 7. And for a rolled section, the flanges aren't the whole story. The web participates quite a bit. So I derived an approximate equation just based on a non-prismatic member, and found that if you put in this reduction that we have, instead of a 10% reduction, it's more like a 7% reduction for the beam that we've selected. Okay, so to analyze the beam, we consider both gravity and seismic. Sometimes the gravity is significant, sometimes it isn't. Here's the distributed gravity load. So gravity gives us a shear at each end of the beam of about 17.5 kips. And then seismic gives us a shear corresponding to the plastic hinge formation at each end, divided by the length between hinges of 44 kips. So we put it together, and on one side that's 62 kips, and on the other side where they offset each other, it's 27 kips. All right, so here's the moment diagram that we'd have if we just had seismic. Here's the moment diagram with gravity, so it's a little bit curved, and you'll notice that on one side of the beam, the gravity is increasing the moment at the column center line and at the column face. At the other side of the beam, it's decreasing it compared to seismic. But for both of these, we've pinned the moment diagram to be equal to the plastic hinge capacity right at the plastic hinge location. So there's the probable moment. That's the same at each side. And then the moment at the face of the column depends on the shear. In this case, the shear is additive with gravity. In this case, the shear is working in the opposite direction from gravity. Here are the values, the larger values, and here are the smaller values. Again, the 70-90 is the same at each end. And as a reminder, we have when we're looking at one connection, we're looking at the left-hand side of one beam and the right-hand side of the other. And so the worst case isn't happening on both sides of the column. The worst case is happening on one side of the column when the other case is happening on the other side of the column. Okay, so the moment at the column face, we've calculated. The moment resistance at the column face is given by this equation from AISCE 358, and we're fine there. The shear is fine. It's much greater than the shear demand. We'll check strong column, weak beam. We have to make some adjustments for the column strength. For the column strength, we subtract out PU over A from FY, but we're allowed to calculate the shear in the column and multiply that by half the beam depth, and essentially to check the column not at the center line of the beam, but at the essentially at the top flange location. So here's the load that we have in the column. Here's the corresponding shear that we calculate in the column, 106 kips. And here's our sigma MP column that includes the effect of this shear. And we do this, something similar for the beam. We've already calculated the moment at the center line, both at the left and right end of the beam. And we do the comparison, and it turns out to be strong column, weak beam is met by a factor of 1.44. The sections that we chose had a strong column or a plastic section modulus ratio of 2.1. So you see the actual strong column weak beam ratio is a bit less, which is why I say keep a good margin like 1.5 if you're going to use this approximate method for member selection. Okay, the force at the column face. This is from AISCE 341 2016. Because of the participation of the web, if we have a welded web, we take 85% of the moment at the column face as being represented by those flange forces and multiply by the distance between flange centroids. That gives us an applied force of 288 kips. Check web local yielding against that. Here's our equation for web local yielding. The bearing length is the thickness of the flange. And it turns out we're just barely no good for web local yielding. We check web crippling. Web crippling works out okay. We check flange local bending. Here's the equation for flange local bending. That turns out okay. In AISCE 341 2010, something that was deleted in 2016, we have this additional requirement for the minimum column flange thickness. If you back solve, it's pretty close to having an applied load equal to 1.5 times RY/FY times the area of the flange. And that would be an applied load of 343 kips, and so it doesn't work out. Also, this equation is both in 2016 and 2010, minimum column flange thickness, 1.03, I'm sorry, it works out to 1.17, which is greater than the 1.03 that we have. And so, for a couple of different reasons, continuity plates are required in this connection. We look at the panel zone. We have the moment delivered by the column on, say, the left, and the moment delivered by the column on the right to the face of the column. I'm sorry, by the beam on the left and the beam on the right to the face of the column. And we subtract out the shear in the column, and that gives us a panel zone shear demand of 937 kips. Our capacity is given by this equation, and that gives us 285 kips from the web of the column, plus 59 kips from bending of the flanges. And we find that a doubler plate is required, and if we solve for that doubler plate, it's about a ½ doubler plate required. Now I will talk about optimization. Optimization. Our current design works. We meet the drift limits. We meet all those limit states as long as we can provide that continuity plate and doubler. So let's look at a different design that provides us the same stiffness that we need, but maybe is a little bit cheaper and doesn't require the continuity plates and doubler. We're going to use a heavier column and a lighter beam to eliminate that reinforcement. So let's say this is the design that we have that requires the doubler and continuity plate. We can look at this as a subassembly from, using the portal frame method, using from mid-beam point to mid-beam point, or mid-column point to mid-column point. If we apply a shear to the column, we get a certain rotation between the beam and the column, and that's a function of the flexibility of both the column and the beam. Well, I'm going to say that somewhere there's another pairing of column and beam that gives us the same stiffness characteristics, but puts more of the flexibility into the beam and less of the flexibility in the column, such that the heavier column and the lighter forces from the beam do not require continuity plates or a doubler. And if I do a bit of algebra, I come up with this equation here, which has if I have my first column, my first design of column and beam, and I compare, say, the allowable displacement that I have compared to the displacement that I actually calculate. I can take advantage of any extra flexibility that I can permit myself. I can solve for the beam moment of inertia that I would need in order to have the equivalent stiffness for this subassembly compared to that subassembly. So that's what I did. I took the initial subassembly, calculated that flexibility, included for the RBS, we have the 0.9 in there, included the actual drift and the target drift. If I up the size of the column from a 14 by 132 to a 14 by 135, it turns out I can't reduce the beam size yet. And I still need continuity plates, and I need a doubler, although it's a thinner doubler. I up the column size again. Still need the W24 by 62. However, I get rid of the continuity plates, and the doubler is very thin indeed. So I'm going to try once more, up the column size all the way from 132 to 176. The beam size that I need, I can go down a size. It looks like perhaps I'm right at the limit. I'll need to put it in the model and check the drift. But I get rid of the continuity plates, and I get rid of the doubler. So that is pretty big. So let's do the little comparison. The original design had 24 by 62 beams, 14 by 132 columns, pretty close to the drift limit. We needed continuity plates and doublers at the fourth floor, but at the roof, we needed continuity plates and no doubler. The optimized design over 3 bays, smaller beams, heavier columns. Our drift is right at the limit. We are adding some steel. That costs some money, but we're getting rid of continuity plates both at the fourth floor and the roof, and getting rid of doubler plates. So all in all, there's a pretty significant savings here. So that's a little trick you can build into your spreadsheets to optimize your steel moment frames. By the way, if you're interested, if we had selected Z column over Z RBS in the neighborhood of 3, we'd probably arrive at something with less need of reinforcement. All right. So quickly now, we'll look at the beam design. Fourth floor beam, we're just going to check the original design, not the optimized design. Very low axial force, we're going to neglect it. Here's the length between the plastic hinge locations. We need lateral bracing. At the top flange, we're continuously braced by the deck. Bottom flange, we're bracing just outside of the plastic hinge zone. And then we have a spacing of lateral braces required. As I said before, it's about 50 RY. The RY that we have is about 1.4, so that's not even 6 feet. So we need to brace about every 5 feet or so. If we had selected a heavier member, much heavier member, we could have bracing, say, at every 7.5 feet. But then we would probably wouldn't meet the, we would probably need reinforcement at the beam to column connection. So the price that we're paying is a couple of extra braces. Here's our lateral bracing of the bottom flange. So we have a moment, including seismic, dead and live. Seismic is amplified by the B2 factor. Here's the moment at the column center line. It's WL squared over 12. Doesn't really, it's not really the moment that we have in the beam, but since our moment capacity is much higher than that, we know that the beam selected is okay. For the first segment outside the RBS, we're going to look at lateral torsional buckling, since our L sub B is greater than L sub P. This is approximately the moment that we have in that segment, 250 foot kips. C sub B is 1.2. I'll refer you to the seismic design manual example to show how we get that. And it turns out that we're fine there. C sub B, by the way, given by this equation, if you didn't have much of a gravity load, if you had a straight line moment diagram like this, you could calculate your C sub B using essentially this equation. So if you had 5 spaces, you'd have a C sub B of 1.2. If you had 4 spaces, 1.25, 3 spaces, 1.33, and so on. Right, now we'll look at a column. Very importantly for the column, or the section properties that we use, we'll be looking at 2 cases. One is the base shear case. The base shear case has the unamplified seismic load. but includes both flexure and compression. So we're going to apply both the B1 and B2 factors. The second case is for the amplified seismic load, and that has the factor of 3, and that we look at for just axial in the absence of flexure. We do need to apply the B2 factor to the axial load. Here is quite small. We're not going to check it. We'll say it's okay by inspection. Axial load dominated. Well, I don't say dominated. It's a lot of seismic, but there's a fair amount of accumulated dead load as well. And then the moment definitely dominated by seismic. Okay, so for the combined axial and bending, here's the axial unamplified seismic, the bending including unamplified seismic. We have a B1 factor. The B1 factor is based on C sub m, 1 minus P over PE. The C sub m has to do with the shape of the moment diagram. Typically, for a special moment frame column, we have reverse curvature. We don't know exactly where the inflection point is, but we know that at worst, our C sub m is going to be 0.6. So if we assume our C sub m is 0.6, our B1 is equal to 1 if PU is less than or equal to 0.4 times PE1. That seems that's almost always the case. So our B1 is 1 for this special moment frame column. All right, continuing on. The axial strength is 1690. There's our flexural strength. We'll get both of these from the manual, and our demand capacity ratio is okay. And we look at the case with the amplified seismic load, axial, no moment, and it turns out we're okay for that one too. All right, so we've checked the strength of the beam and the strength of the column. Turn to the base plate design. So we're going to look at this base plate, so the same base plate, or the base plate that corresponds to the column that we just looked at. It's going to have a fair amount of overturning on it, so compression and or tension. And again, here are the column section properties that we use. All right, the overstrength forces will apply for reasons that we'll discuss as we go through the design. Ductility is still helpful. In a lot of cases where we design for overstrength forces, we think because we've designed for overstrength forces, the member won't yield. But here at the base of the column, you can't really get to significant drift if you don't have some rotation at the base. So ductility in the connection or the member is still pretty much required at the column base. We're going to definitely consider the tension case and follow the Design Guide 1 method. So this is similar to example 4.43 in the Seismic Design Manual. In the Design Guide 1, it's the base plate with large moment method. All right, so the first thing we do is line up our forces. We have just very small shear due to dead and live because it's a rigid frame, but most of our shear is due to seismic. And again, we apply B2 to the entire lateral analysis, and that gives us a shear demand of, for the entire base plate of about 28 kips. Axial load, we've got dead, live, and seismic, including that B2 factor. And then moment, again, a little bit of dead and live moment, but mostly due to seismic. All right, looking at the load combination with uplift. So we're assuming the axial load is pulling up from seismic with a reduced pushing down from dead load. The shear, including this overstrength factor, 85 kips. The tension, about 60 kips. And the moment, about 635 foot kips. This moment is well below the expected column strength. So right now it looks like the demand on that base plate is going to be a lot less than the demand that would cause a hinge in the column. We'll come back to that later on after we've done the design. All right, so here's a column. There's the base plate. We're putting anchor rods to hold it down for both tension and flexure. And of course, we have the anchor rods on both sides because the flexure can go either way. So 4 anchor rods here and 4 anchor rods here. Dimension here of 32 inches. Width here also 32 inches, I believe. We make the assumption that the effective depth of this column is 95% of the full depth, so maybe the uplift from the flange is centered here, or the cantilever distance, say for the tension rod pulling down, goes from the center of the rod to this point here. There's our moment, and there's our axial force. When we have equilibrium here, we have some tension in this anchor rod, and we have some compression over a length here on the grout underneath the base plate. That width of that, or that depth of that compression block is given by this symbol Y. Okay, so how much compression can we put into that grout? We use this equation from ACI. It includes the square root of A2 over A1 that essentially lets the stress spread out from the contact area to a larger effective area. And with the strength that we have in the concrete, it permits us to go up to about 4.4 KSI. Take that over the width of 32 inches, and it's 141 kips per inch. We're using an effective eccentricity just calculated by taking our maximum moment divided by the tension that we have here, and that's an eccentricity of 128 inches. So we can calculate based on that information the length Y that would satisfy equilibrium, and that length Y is 1.8 inches. So this is the method shown in Design Guide 1. Okay, and so that 1.8 inches of compression times that 141 kips per inch, that's essentially like a prying action, which increases the forces in the bolts. So we have the tension already in the column, and then we have this compression, and all of that has to be resisted in tension in the anchor rods on the other side. So that's about 79 kips per rod. Okay, so we'll continue with the design, looking at these dimensions here. Again, it's 32 by 32. Calculate these N dimensions and M dimensions based on the section that we've used. On the bearing side, where we have that compression stress pushing up, we have bending in the base plate, and this equation essentially gives us the thickness, considering the Fy of the base plate, for which the flexural strength will be sufficient. And that gives us 2.51 inches, and I guess somewhat conservatively we're saying use 2 3/4 inches. Some people might say we're so close to 2.5, let's use 2.5, but we're going to use 2 3/4. On the tension side, we do a similar equation, but we consider essentially the tension pulling down times that eccentricity, and that gives us 2.1 inches. So the other case governs. All right. For efficiency and simplicity, we're going to make the assumption here that under this loading condition, we have 4 anchor rods that are working in tension and not taking any shear. And then on this side, perhaps we have 4 anchor rods that are working in shear and bending, and obviously they don't need to take the compression, so that's all that they have to do. The shear is that full 85 kips divided by 4 bolts. And the moment has to do with the eccentricity, and the Design Guide 1 gives us a little formula for that eccentricity that includes the half the thickness of the washer plate, thickness of the base plate and the thickness of the grout, and that gives us a corresponding moment. All right, so we have different anchor rods to check. We're going to check the anchor rods in tension first. And if we select an 1.5" anchor rod, we have a certain effective area. In gray are the things related to bending and shear that we're not using. And it turns out that we have the 1.5" anchor rod works for tension. Now we'll check the other anchor rods, the ones that are working in bending and shear. It turns out for these we need 2" anchor rods to handle the bending and shear. And those just barely work out. All right, so designed for tension only, we could make work with 1.5" anchor rods, utilizing the net section. If we used shear and bending in the anchor rods to take out the shear in the base plate connection, we would need 2" diameter, and obviously we'd use 2" diameter for all 8 of the anchor rods. And rods really aren't that great of a bending element. If we made a really conservative assumption and took that shear over all 8 of the anchor rods so that we'd have combined tension, shear, and bending in 4 of those anchor rods, they would need to be 2¼ inches thick. I would certainly not recommend that. So what I would recommend is just designing the anchor rods for the tension and taking the shear out, not via the anchor rods, but some other method. If we have this whole thing encased in concrete, it doesn't take a lot of bearing area to take out the shear. So if we took just the thickness of the base plate times the width of the base plate, we could resist 211 kips of shear. Obviously, we'd need to complete that load path, but it is certainly a load path that's available to us. Another way that people often take out shear is calculating friction based on the compression that's present. Now, the compression that's present isn't just the compression in the column, it's the compression due to flexure, which is pushing down on the toe of the base plate. That was that 141 kips per inch times that dimension y of 1.8 inches. That was over a couple of hundred kips. And then if we have a shear coefficient, a coefficient of friction of 0.4, that gives us 102 kips of shear capacity, which is sufficient for our design. So we've got a couple of very easy load paths available to us. You could also weld things to the base plate and drag them out. If you are using bearing, you almost always face a condition where you're at the edge of the building and you have to make sure that you have a load path for taking that shear out at the edge of the building. Say if it's bearing, you need to drag it back somehow into your slab and foundation in some detail that might look a little like this. These rods then, if we're taking the shear out not through the rods would be designed for tension only. I always think it's a good idea to provide a debonding mechanism for the rods so that they can elongate a little bit and allow the connection to rotate and provide some ductility. The anchor rods that we're using are grade 55. The washer that I'm using for this example is greater than the washer that's called for in Table 14-2 of the AISCE manual. So we're using 1.5" grade 55 rods. I always recommend using the supplement S1 that allows for welding of the material, so that gives us better options if the anchor rods are mislocated or damaged in construction. So here's the washer plate that we're using. The concern for the washer plate is that it might dish and create greater flexibility than we might otherwise have. I will say that this recommendation is one that I've given before. I've discussed it with various people in AISCE and elsewhere, but there doesn't seem to be any publication of test results that we can point to. Nevertheless, it seems prudent to consider the grade of the anchor rod in sizing this plate. So if we have grade 36, I say use the thickness that's in the table. If we have grade 55, use something that's at least 40% of the diameter of the rod. And grade 105, more like 70% of the grade of the rod. And that adequately addresses the potential for dishing. Now, looking at potential ductility demands as at this connection, where is the inelastic rotation going to come from as the frame goes out to, say, 1 to 2.5% drift? Well, the inelastic rotation could come out of the column, but as we saw before, the column has significant overstrength. We could get some inelastic rotation out of the elongation of the anchor rods, which we debonded. But remember, the anchor rods are designed for that one case where the column has significant tension. If the column doesn't have tension, in fact, if the column has compression, it's going to take a lot of moment to even begin to load the anchor rod. So that moment is about 300 foot kips before we start engaging the anchor rod based on the axial load in the column. Base plate flexure. Similarly, we have a base plate that might be selected very close to the demand, but the demand corresponds to the tension case, and it's going to take a lot of flexure to overcome the compression on the column. It could also come out of foundation rotation, and we haven't presented any foundation design here, but maybe that's a good source as well. Okay, so the column strength, again, RY, FYZ, almost 1,200 foot kips. The anchor rods, well, if we use the 1.5-inch anchor rods, it would take about 1060 foot kips to begin yielding those, and that includes what it takes to start lifting up the column when there's significant compression on it. If we use the 2-inch anchor rods, we'd be all the way up to 1660 foot kips. So you can see that if just a little bit of conservative design there, and the anchor rods couldn't really provide any ductility before the column yielded. So maybe the yielding of the column is the way this thing is going to behave, at least when the column's in compression. And at the base plate, again, that because we use the 2 3/4-inch base plate, that actually gives us a pretty high flexural strength before it starts to yield. Okay, so with the 1.5-inch anchor rods, we have significant overstrength, even though we were trying to design everything absolutely to the minimum. The 1.5-inch anchor rods still give us significant overstrength. They do not protect us from the possibility of column yielding, so we should take the column yielding possibility as a very real condition. So we'll CJP the flanges and fully develop the web. All right, so with that, here's our more or less final design. We're doing the CJP of the flanges, demand critical welds, CJP of the web. Again, demand critical welds are called for by AISC 341. And then we have the anchor rods, 1.5 inch, and they're embedded as far down as they need to be per the foundation design to make sure that we can develop the force into the foundation. And we've called for debonding of those rods from the concrete, so that all of the force has to be delivered at the bottom via these base plates double nutted to the anchor rod. So that's our example moment frame design. What didn't we get to? Well, we didn't fully detail the connection showing the demand critical welds, where we're removing the weld tabs and removing the backing plates and so on. All of that is detailed in AISC 358. We didn't indicate the protected zones or design those lateral braces. We got the spacing of them, but we didn't determine the required strength or details of them. And of course, there's a column splice to be located and designed. For the base plates, we mentioned that we had to provide a load path for shear, but we didn't actually design that. The concrete anchorage for those large tension forces also has to be designed. And the grade beam has to be designed as well, and perhaps that's where we're getting some of our inelastic rotation from. Specifications, we need to specify the weld toughness requirements for the lateral load resisting system and what we mean by the demand critical weld, and a quality assurance plan. So all of those things are necessary to complete the design, but I think our example covered quite a lot in the 90 minutes that we had available. In summary, the special moment frame tends to be governed by the need to control drift. So I recommend sizing members to control drift first, and then you can make some very conservative assumptions in your strength check, and those generally don't affect the design. You could assume C sub B of 1 and C sub M of 1 and still calculate demand capacity ratios well below 1. You can also combine a number of checks, just looking at, say, the worst case moment in conjunction with the worst case axial, and save yourself a lot of detailed calculations because, again, the demand capacity ratios tend to be very far away from 1 for the strength checks. Selecting heavier columns initially tends to reduce reinforcement and make for a generally more economical design. So with that, we arrive at the end of session L3, and next week we'll complete the example with the design of the braced frames. Finally, I'll remind you that we did refer to a couple of other resources. There's the NIST Tech Brief number 2. Now in its second edition, that's a free download from NIST. You can look it up. EHRP Seismic Technical Brief number 2 should be the first thing that comes up. And then there's Farzad Naeem's Seismic Design Handbook. We referred to that for just a couple of things, but it's a pretty comprehensive and very useful resource. Finally, we arrive at question time.
All right. Thank you very much, Raphael. We will get to some of the questions that we have coming in from the audience. And as a reminder, if you have a question that you would like to pose to the speaker, please type the question into the chat feature on your screen. But we're going to go ahead, and as we have done in the past weeks, we're going to do a couple of interactive polling questions to test the audience's understanding on a couple of concepts. So here's the first interactive polling question. This is a true or false question. And the statement is this: the AISC 358 recommendation to increase the overall drift by 10% to estimate the effect of an RBS connected moment frame is typically conservative. Is that a true or false statement? Once again, that statement is the AISC 358 recommendation to increase the overall drift by 10% to estimate the effect of an RBS connected moment frame is typically conservative. All right. Nearly all of our answers have been provided by the audience, so I'm going to close the poll. And almost a nearly unanimous choice by the audience was that this is a true statement. Did they get that one right, Raphael?
They did. I said it often enough, it must be true.
All right. Well, good job, everyone, on that one. Let's go ahead and move to the second one. Multiple choice. What is maximum depth of a wide flange shape that can be used for a beam in an RBS connection? Answer A, W18, B, W24, C, W36, or D, there is no limit on the depth of a wide flange section. Once again, what is the maximum depth of a wide flange shape that can be used for a beam in an RBS connection? All right, I'm going to go ahead and close this poll. And it looks like nearly 90% think the answer to that one is C. Did they get that one correct, Raphael?
Yes, they did. Very pleased.
All right. Good job, everyone. So we'll go ahead and move into a few questions that we received from the audience. And our first question is going to send us back to slide 41. And the question is this: is the drift limit used in this example for a building that is considered fully cladded with glazing?
Yeah, so we discussed this a couple of weeks ago. In the drift limit, the ASCE 7 minimum or maximum drift for this building could be 2.5% because it's only a 4-story example. So we could have gone up to 2.5%, but because this is a building with cladding, going out to 2.5% means that the cladding has to be detailed to accommodate that drift and still perform without life safety hazard. So we've arbitrarily limited it to 2% in order to permit the design of a more economical design of the total building rather than just going out to the maximum drift limit.
All right. For our next question, we're going to move to slide 43. And the question is this: there is this load combination that you show here with a 1.0 for the factor for dead. Can you explain where this load combination is used in comparison to the load combinations used later in the presentation with higher load factors?
Yes, so this is an interpretation. So for strength design, the standard load combination would include 1.2 dead plus 0.5 live and so on. However, for stability design, if you look at the section ASCE 7, section 12.8.7, when you're looking at P delta effects, the code says you don't need to consider any load factor greater than 1. I know that there are some engineers who would put 1.2 dead in this equation rather than 1.0 dead, but I'll just point out that the lateral load that causes the first order effect, so the seismic load that we're calculating, is based on 1.0 dead. And it seems inconsistent to me to use 1.2 dead for a second order amplifier on that and use 1.0 for the first order force. So I'm just being consistent with the mass that's used to calculate the first order force. If you wanted to have some safety factor on that, I think you would apply the same load factor or the same factor on the mass used to calculate the primary force and the mass used to calculate the second order effect. I hope that's clear.
All right. Let's move to slide 91. I had a couple of questions on this section on base plate design. And so the first one is it appears in this that there is a pin connection at the base of the column. And so how did you determine the MU for the design of the base plate?
So in the model, there is in fact a pin connection a pin connection to the foundation, but there's a fixed connection to that grade beam element. So there is that grade beam is a stiff flexural element, and the column goes into reverse curvature. So the stiffness of that grade beam is intended to model the finite rigidity of the foundation system. So it's not modeled as infinitely rigid, but it's not modeled as infinitely flexible either.
All right, we're going to stay right here for the next question, related question actually. Is it acceptable to assume fully fixed or perfectly pinned base of the column in an analysis?
So it is, according to AISC 360, if you have a pin assumption in a connection, you have to be able to accommodate the rotation involved. And I don't see that as a very realistic way of designing for the base of a special moment frame. So it's probably conservative for selection of your beam and column sizes, but in the end you have to design that connection to perform under large lateral loads and large lateral drifts. And so I don't see how you can actually accommodate that inelastic rotation in a so-called pin connection. I suppose, well, I haven't seen such a design. I suppose there are different methods where you could allow some rotation, but those would be unusual connections. As for fully rigid, that might be a little unconservative in terms of member selection to meet your drift limit. But in some cases, perhaps the foundation system is so stiff that its flexibility doesn't really need to be taken into account of. But for many foundation systems, there will be some flexibility, and that flexibility will contribute to the drift of the first story. And so at least that should be considered in determining whether to model it as fully rigid or select some reasonable rotational spring for that support condition.
All right. Our next question, we're going to go back again in the presentation to slide 38. And so the question is there a special reason why the importance factor ends up being in the denominator of the expressions on this page rather than the numerator?
So what we're doing here is really calculating. Well, we're taking that C sub S factor, say in the top equation. That C sub, it's not a factor. That C sub S value. That C sub S value has been already divided by R and multiplied by I sub E. So all we're doing is pulling that out. So in that top equation, if you could simply go to the right-hand side where we're taking SD1 and dividing by T and not modifying by R or I sub E. So I'm just pointing out that it's like the code equation, but it's assuming that R and I sub E don't modify it at all.
All right. Well, thank you very much for those answers, Raphael. That's actually all the time that we're going to have for getting to